Hello, in this video we are going to continue to learn how to use the conceptual model approach to build mod flow models in GMS, and this is the first of a four-part series of tutorial exercises based on a site in East Texas. This is an actual location, although the hydrogeology and the parameters and the other things have been just made up numbers to make this a simple model that we can solve over the course of a basic tutorial exercise. And so this site, in terms of a conceptual model, it has a river that goes along the bottom of this region from west to east, and then there's a creek that runs down this side. And then there's a limestone outcropping on this side, and so we are going to simulate some alluvial sediments here, the groundwater flow and alluvial sediments here in this middle part of this image. And in this exercise, like I mentioned, it's going to be done in multiple steps. In this first part, we are going to build a model that follows these boundaries. Now this north part, the limestone outcropping, will be a no-flow boundary. And the river here, it says you have three options here. It could be a river package, or you could do specified head, or you could even use a river package. Originally this tutorial was set up to use specified head, so that's what it says on this diagram. The current version of the tutorial has us do it as a general head condition, which is fine. Any of those options would work, just depending on what assumptions you want to make. And so in the first iteration, we're just going to simulate a single hydraulic conductivity zone over the whole model. We'll use just a simple flat top and bottom, and have the river boundary conditions as I mentioned. We'll have recharge coming in, and we'll build the grid, convert the conceptual model over to the grid-based input, and that would conclude this part of the exercise. Later we will add the wells and partitioned recharge. The use case that we're describing here is there's a proposal. We're assuming there's a proposal for this for a landfill in this location shown here, and the model in subsequent tutorials is used to perform particle tracking and transport modeling from the location of this landfill to see what the impact would be. So in one of the later tutorials, we put that landfill in and adjust the recharge in that area, also the wells. And then these creek beds are a series of 3 creek beds that go through the model, and these can be represented as drains, and those would be added in a subsequent tutorial. Later on, we'll also interpolate top and bottom elevations, convert it from a 1-layer to a 2-layer grid, and do some interesting things with the wells and how the wells span multiple layers. So this is we're going to be following the Aquaveo tutorials. If you click on this link here that's in the main mod flow section, conceptual model approach 1, 2, 3, and 4, we're doing the part 1. There's a PDF file associated with this. There's also a zip archive that has some input files we're going to use to get started. And so I have already downloaded those files, and I'm going to open GMS here, and the files are located here in this modf map1 directory, and there's a start.gpr. I'll open that up, and what you're going to see here is this is a scanned image from United States Geologic Survey topo map, which has been imported and registered. And years ago we scanned a topo map and brought it in, and we're using this as the background. Now This corresponds to a real location, and this background image, we're kind of skipping over how you'd go about bringing in an image, but there's a process by which you bring in an image and then identify some coordinate locations on it and type in their real world lat long coordinates in it and select a projection, and it drops it in. Nowadays, with the availability of web services and base maps, we don't normally do it that way. What we typically do is we use the add online maps utility, and it doesn't bring out, normally when you do that it brings up the map locator, but since we already have some data in a particular projection, it knows where we are. So all we have to do now is pick one of these map options, and you know, there's a real base map of the actual location. Now this is a street map, but you can see here's the creek down one side and here's the river down the other side, and we're going to be modeling this region right here. We can do this again if we want and bring in imagery if we want to get another look at this. So again, here's the creek down one side, the river on another side, and here's our alluvial fill here in the middle. We have this outcropping over here on this other side that we could simulate. And when you bring those in, you can kind of switch back and forth between those just by using the toggles over here. And but to keep it consistent with the tutorial exercise and instructions, I'm gonna use this base map here. But just wanted to point out that there are different types of base maps you could use for this exercise, and it would work just great. So now that we've made some changes, I'm going to do File, Save As, and I'm going to call this, let's see, let's call it easttex1.gpr, and we'll save that. And then, okay, the next thing we're going to do is we are going to create a conceptual model object. And we'll call this East Texas. And then we're going to, as we mentioned in our last exercise on the Big Lake exercise, it's a good idea when you start out building a model using the conceptual model approach that you start out by creating a boundary coverage, which is just a single arc that goes all the way around the perimeter of your model. And then the reason you do that is then you can make copies of that boundary coverage and then use that to for your other coverages to ensure that you have the same boundary on all of them. And so here's the instructions. We're going to start here and digitize along this lower boundary and up the right side and back over the top. And so here we go. I'm going to go to the, well, first of all, before I do that, I skipped a part. I need to create a new coverage, which we'll call a boundary coverage. And then I'm going to use the Create Arc tool. And I'm just going to follow along this boundary down here. Along this river, I should say. I'm just clicking out, and every time I click, that creates a vertex, which defines the geometry of the arc. Now I'm going to get over right here at the junction of these two rivers, and I'm going to double click. Whoops, let me backspace one. I'm going to double click. I want to make sure that I have a node. I want to have a single arc along this boundary. I want to have a node here so that I can specify the head at that location. And then I'm going to go up this side here. And you can, it doesn't matter if you follow this terribly closely, but I'm going to go right here. I'm going to double click again because this is going to be another kind of boundary, or a separate boundary, and I want to be able to specify the head right here. Now from here over to where we started, this is a no flow boundary condition, and so I just need to trace out the the location here. I'm just going to kind of follow along on where these contours kind of indicate that it's raising in elevation. And we'll just keep going. Maybe curve around like this. And then I'm going to go back and click right there. So now we have these 3 arcs that we've created. And we could save our changes. And we are ready to go at this point. Okay, now normally at this point we just keep going, but you know, according to the instructions on the tutorial exercise, it says, well, to ensure that we have consistency across the tutorials, they want us to read in a coverage that someone else has digitized for us. So we're just going to we're going to delete that conceptual model, and then we're going to go File, Open, and there should be, if we change the filter here to all files, there's a folder called boundary.map, M-A-P, and what that is let me turn off the background again. So this is a single arc. It's a boundary coverage essentially. Let me expand that. So it's a boundary polygon, and it's been digitized for us, and we're going to use this going forward. So now we know how to digitize a boundary arc coverage, but we're going to use this one going forward. Now the next thing we're going to do is we're going to mark these boundaries down here and up this side as excuse me, general head arcs, and assign elevation. Now again, you could use specified head boundary conditions. That assumes you have a direct hydraulic connection without any significant barrier to flow between the river and the aquifer. Or you could use a general head boundary condition, which allows you to specify a conductance of, say, your river bottom sediments, and that way you'd lose a little bit of, there's a little bit of a head loss as the water goes between the aquifer and the river, and it can either be a gaining river or a losing river. So it's very similar to a specified head boundary condition. In fact, if you have a really large value of conductance, it becomes virtually identical. The other option would be to use a river boundary condition, or the river package, which is similar to a general head boundary condition, except that, or the general head package, except that if the water table gets below the bottom of the river, then it becomes a disconnected river and the flow rate is fixed. But we're going to go with the general head option for this one. And before we do that, you know, when I was digitizing this, I put a node right here and right here, and that wasn't done in this case, but that's okay. If you turn on the Select Vertex tool and you right click and say Vertex to Node, all right, there's a little projection issue it had to resolve, and there we go. So now, whoops, now did we still have, let me try that again. There we go. So now we have, if you use the Select Arc tool, we have 1, 2, 3 arcs. This will be general head, and no flow. Remember, in the term, when we're modeling, a no flow boundary condition is simply if you do nothing, it's a no flow boundary by default. So we don't need to do anything for that. But all right, before we get too carried away, we're still working on the boundary coverage. We need to duplicate that, and that creates a copy. We'll double click on that and call that rivers. We'll turn on this general head option. Okay, and when we do that, we will now I'm going to click here. I'm going to use the select arc tool. I'm going to click on this arc, and I'm going to hold down the shift key and click on that arc. So I've done a multi-select of these two arcs. I want them both to be river arcs. So I'm going to right click and select attribute table. I'm going to change the type to general head. And now we need to input a conductance, and it says to use a conductance of 0.1. It doesn't really provide any background, but basically a conductance for all of these packages that use conductance, it's Ka over L, where K it's like the non-head terms in Darcy's law, the hydraulic conductivity, and it describes the material between the aquifer and the object. In this case, it would be the river bottom sediments. So the K would be the hydraulic conductivity of the river bottom. The area would be the cross section of flow across whatever reach of the river you're looking at. And so that'd be like looking down in plan view. It'd be like the width of the river times the length of the river. And then the L on the bottom would be the length of flow, and that would be the vertical thickness of the river bottom sediments, because the water is going vertically between the two, between the aquifer and the river. But when you enter a conductance in GMS in the map module, it has to be a conductance per unit length. So it says meters squared per day per meter. Meters squared per day are the normal units for conductance. And so to get that, you take that Ka over L term, and for the area part that includes the length of the river reach, you'd factor that out. So it would just be K, the hydraulic conductivity of the sediments, times their average width divided by their vertical thickness, and that calculation's been done for us. But it's important that you understand how those calculations are done. Now these are then designated as general head cells, or rivers, or excuse me, general head arcs as part of our conceptual model. And the next thing we want to do is click on the, we need to assign head values to these three nodes. And then the head will then vary along the length of the arc, and the head values are given to us. I'm going to use this select point node tool, and I'm going to double click right here, and that'll bring up the attribute table where I can enter 212 for that node. And this one over here is 208. This would be the head or the stage, and then down here we're going to use 214. So it's fairly flat here, not a lot of elevation change. And so that defines our rivers. And now if I go back to the coverage setup for this river package, you notice it says used to define model boundary active area. You need to have one of your polygons that or coverages needs to have this on. And then, but we also need to go into the feature objects menu and select build polygons. And so we had a closed loop here, and when we did build polygons, it created this polygon. And we don't need to assign any attributes to it, but this defines the active region for our model. So we're going to save those changes. And now we're going to create another coverage to define our hydraulic conductivity and our top and bottom elevation for this grid. So we're going to right click on the boundary coverage and select duplicate, and we're going to call this aquifer layer 1, and we're going to turn on horizontal K, top and bottom elevation from the aerial properties. Okay, and then we need to do build polygons, because we're going to have a single polygon here where we assign these properties. Now, you know, later in this exercise, we're going to split this into zones. Well, actually, we're going to have two different layers, but you could subdivide this polygon into a bunch of subpolygons and assign a different hydraulic conductivity to each one. But we're going to keep things real simple here. And so I'm going to double click on this polygon now. And now we can enter 5.5 for the hydraulic conductivity, 230 for the top elevation, 175 for the bottom elevation, and save our changes. And we are doing really well. Okay, now normally what you do at this point is create a recharge polygon, enter recharge, as that's one of the most fundamental parts of model input. And I mentioned that earlier that we'd do that, but I actually misspoke. That we're going to do that in a later version of the tutorial. So we are now ready to create our grid frame, which defines the location of our model grid. And the way you do that is you go over here, you right click and you select new grid frame, and then you use the grid frame tool. Now by the way, you can right click on this and say fit to active coverage, and it will automatically stretch itself to fit your model. And I actually like to squeeze that in just a little bit. I think it goes a little too far. There we go. That should fit. And now we're ready to say map to 3D grid, and we are going to tell it, instead of the number of cells, we're going to give it a cell size of 20 meters in X and Y. Leave a one layer one layer in Z, and that gives us our grid. Save our changes there, and next we will initialize the mod flow data by selecting new simulation, and we'll just accept the defaults there. And then we say activate cells in coverage. That turns off everything outside our grid. And we say map to mod flow, and click OK, and that maps over our boundary conditions, our hydraulic conductivity, top and bottom elevations. And now let's do check simulation, and everything looks good. So we're going to save this one last time and then run mod flow, and there we have it. So we have water coming in over here and over here probably, and then leaving down here in this part of the model. Again, we haven't added recharge yet. That'll change our flow budget, but if we go look at our flow budget for a second, you can see we have, well, that's not going to tell us too much. We have the same amount coming in as is going out, which makes sense, and they're all through the same type. I was going to see if we could see how that's distributed, but you can kind of tell based on the elevations that there's water coming in here, here, and then going out through this lower part of the model. So that's it, really simple. So I can turn that background image back on, or one of our other two images if you'd like. And so what did we do? We created a boundary coverage, we copied that, created river coverage that had our rivers and defined our active region, created another coverage that had our hydraulic conductivity and our top and bottom elevation, created a grid frame, created a grid, activated the cells in the coverage, and then mapped over our data and saved and ran mod flow, and everything seems to have worked out successfully. So that completes the first step of this 4-part exercise.